So I'm Vasilos Karakasis, and I'm gonna give the lectures this morning. The program is, as usual, we're gonna have a break at 10, and then at lunch. So at the beginning, I'm gonna start with an introduction about the GPU architecture, and then we're gonna move into hands-on examples with Numba and GPU. I'm here. It's now I can start sharing my own screen. Thanks, Tina. Okay, so until I share my screen, I'm here at CSCS. I'm a computer scientist, and I'm currently leading the scientific computing support team. And yeah, that's about me. So I think, let me know if any panelists, if you can see my presentation. Okay, before starting though, I would like to pose a question to the audience, and I think I need to stop sharing first. Yeah, so yeah, please respond to this question. So how familiar are you with CUDA and GPU programming in general? Just to give me a bit of understanding of. Okay, I end the poll. So, okay, so that's nice. We have yeah, most of the people know a little bit or not at all. So I will try to keep it quite introductory, and yeah, feel free to raise your hand if you have questions, or type your question in the chat, and I will try either to answer live or somebody from the panel, or I will just give you the mic to ask the question live. So let's start. Okay. Just a second. Okay, please. Okay, so the first lecture is yeah, some introductory slides about the GPU architecture. So I'm going to start with differences, what are the key differences between the GPU and the CPU, what is the execution model, and what is also the memory model. And the second part, after the break, we're going to see all these concepts and put them in practice with Numba. So, I mean, you might not be yet.
Just to interrupt you. Can you give a hands up or a thumbs up if you can see the slides okay?
Yeah.
Okay, great. Thank you.
Okay. Let me also, that's perhaps better for. Okay, that's better here. So most of you are already a bit familiar with, already quite familiar with CPU. You're using them all the time, but most of you perhaps are not so much with GPU. So there are two big differences, I would say. One is that the CPUs are really optimized for low latency access to, for low latency access to basically to memory and to random access in memory. So to achieve that, they have very big caches. So they have not so many cores compared to the GPU. Okay, now you can find in orders of 10, but again, there's not so many cores. Most of the die area is really dedicated to caches and to control logic. By control logic, I mean that the cores in the CPUs are quite complex. So they support out-of-order execution of instructions, so that the instructions, for example, they do not proceed in the order of the program, because that's would give you higher throughput in the instruction. Also, there's techniques such as speculative execution. For example, when your program there is a branch in your program, then the hardware will just decide, okay, I'm going to take this branch because it's most likely to be taken. So it starts executing down that path. So, but all this requires quite a complex logic, and eats up lots of energy and eats up lots of die area. But the good thing about it is that it serves a wider range of applications. You can run like your web server, your database server on CPU, and you can also run your simulation. So it's really wide. You can also run your operating systems. All these have really quite different requirements. And that's why CPUs are kind of optimized to support this diversity. On the other hand, CPUs are really take a quite different approach. So they really optimize for data parallel and throughput computation. So most of the die area is really eaten up by actual compute units. So this green squares blocks in this slide. And also, I mean, there's not so many caches, so it's the latency to the memory is mitigated through different ways, through parallelism. We're going to see that in a moment, in a moment, and that actually has implications on how we need to program the GPUs, as we're gonna see. So let's see, for example, how a program executes on the CPU. So, or multiple threads. So usually on the CPU, you have, again, thousands of threads running, right? So different applications, the whole operating systems, and your simulations among the others. So how does the CPU meets this parallelism? So essentially what it does is, it puts as many threads on as many threads to run as cores that it has, and then it between different time steps it really switches the context, and that's a work done by the operating system. That practically means that every time, for example, here, that one thread needs to be swapped out, and another thread to come in the CPU for execution, the operating system must save the state of that thread in memory. That means save all of its registers and then bring in another thread to run. That's called context switch. And as you can see that usually the CPU cores has really low latency because they have big caches. So the idea there is that when you miss a request to the memory, then the program need not just wait for the memory to get it. It will get it from the cache memory, from the different levels of the cache. And there you mitigate the latency, so you don't have, because you have very big caches. And the other thing is the caches in the CPU they're kind of connected between each other, in the sense that if one thread writes on a cache, one thread of one thread of an application writes in the cache, then that change will be visible by other threads. So that's what is called coherency protocols, and that's really it's up also energy and die area, but also makes it much easier to the programmer to program. On the other hand, with the GPU, you don't have these amenities, so you have multiple threads and or set of threads. We're going to see them in a moment. So in order to hide the latency, your programs should really expose parallelism, so that the hardware when one of your threads or block of threads encounters a memory stall, so it asks for it does a memory access and does not find it in the cache because the cache is very small, has to go in the memory, then it cannot proceed. Then another thread must be ready to run, and then the scheduler on the hardware will schedule that thread. So the more threads you have, then the more you can hide your memory latency. One other thing to notice here is this little thing, connecting thing between the different CPU threads, especially when we have oversubscription of threads on the CPU, which is the context switch. So there is no such context switch in the GPU. So the GPU cannot, all the threads that they're actively running on the GPU are present on the GPU. So their state is present on the GPU. So there's no operating system that will save the state of one of a thread of a thread on the GPU and move in another thread. This is something is not happening on the GPU for a good reason, which we're going to see in a moment. Because it really helps you to schedule many threads on the GPU. So as you've seen, as we just seen before, on the GPU, it is really crucial to have high parallelism. Now, that really depends on the application, and I would say two things. One is whether there is inherent parallelism in the application. So some applications may be what we call inherently serial. So they have data dependencies that basically cannot be parallelized efficiently. But if your application exposes parallelism, then the program that you write must also take advantage of this. So, because I've seen for the GPU, not being parallel enough, basically it's a waste of resources, and you're gonna be hitting the memory barrier essentially, and not being able to proceed fast with your computations. So there's, for programming such type of devices, there's new programming models and new algorithms, and we're gonna see that in a moment. And also in the second part, we're gonna program in Numba CUDA. You will see that it's a bit different in mentality compared to what you know already from the CPUs. You will need to start thinking more parallel, because what we have been used to with CPUs is that we think and we reason about programs in a kind of more serial, let's say, way. I mean, the implication for that is that existing code has to be rewritten, or generally refactored, parts of it to be rewritten, especially the performance critical to take advantage of the GPU, which entails some manpower cost. I mean, as a result, if you just take your application and do a naive porting, or don't invest time in understanding the GPU architecture, more likely you're going to be underutilizing your allocations. And I mean, the good, but we have somebody saying that he's still seeing slide 3. I'm on slide 5. I don't know. Can team from the panel?
Yeah, I'm also struggling. I was struggling at the beginning. It seems like there's some sort of latency, or I also can't see your cursor moving around if you're moving it.
Okay, let me then try the following. I will try to do the.
Try sharing it in a different way, maybe.
Yeah, from a different application, perhaps. I'm going to try with. Okay. Where do I have it? Okay. Okay, can you see now? I'm gonna make it again into full screen mode. So that's slide number 3. I'm on slide number 4.
No, from my side, it's the same. It's not not advancing.
Okay, so if nonetheless, if now you can see slide
okay,
number
now
4.
It's advanced.
Okay.
Yeah.
Okay, I'm gonna have it like that then.
Yeah. That's better.
Okay, so I was saying that one thing that you can say as good or bad thing is that the parallelism is going to increase. That's for me certainly a good thing because it's the only way you can get forward with more performance. On the other hand, that will make it tougher and tougher for programming. And actually now there's still lots of research and lots of work going on in trying to propose more easy programming models that would hide the details, but still it's something that's being explored right now. It's not something that we have been used to quite established practices, but now this so big parallelism that we have that it really shakes the things. But this is quite interesting as we're going to see also in this presentation. So that's actually how the GPU looks like from an architectural point of view. You can't see much, but there's a couple of things to notice. So notice basically all these many little green boxes that you practically almost see. These are actually the compute cores. It's like the cores of the CPU. But now look at how many they are. So that's a huge big difference between the CPU and GPU. And then you have a common L2 across the whole GPU, and then you have channels for PCI and connecting to the memory. That's pretty much like you would have, for example, in a socket of a CPU. But let's zoom in a bit. So to one of these blocks of cores. So this is what is called what's presented here is the core of the GPU architecture. So this is called the SM architecture, which stands for streaming multiprocessor architecture. And you can view that, I would say the equivalent of that is, in terms also of complexity, is the CPU core. Although it looks like more like having more cores in an SM, which is essentially true. But conceptually, not conceptually, but from complexity-wise, it's more like the core. So what is inside the SM? So first, inside the GPU, there are multiple of those multiprocessors. So what's inside in the multiprocessor? So first of all, there is lots of, there's 64 single-threaded cores. 64 on P100 in older GPUs were less, in newer can be more. But in principle, there is a number of cores. These are very, very simple cores. They really don't have any logic about out-of-order execution, branch prediction, all these things. They're simple cores. That's why they don't eat up so much space on the die, so you can put lots of those. And one key thing is that the execution, those cores execute code synchronously in batches of 32 threads. So 32 threads per, or cores always execute the same instruction. So if, for example, load instruction, then add instruction, and so on, they can't proceed independently. So you can view that as a vector or a SIMD register or a SIMD execution unit in the CPU, where the same instruction, for example, is applied in a multitude of data elements. But here is the same instruction is applied on 32 elements. So another thing is that there is a very big register file partition per core. So this is 256 kilobyte register file, which if you do the division by, for example, 64, it should give you like, thousands of registers, of double precision registers. Now, we're going to see in a while why such a big register file is needed. Then there is what is called the warp scheduler. So the warp is this set of 32 threads that all execute the same instruction. So in HSM, there is a scheduler of those warps because there might be several warps that they wait to be executed. And if you remember from the slide I've shown you before, you need lots of threads to be available, lots of warps to be available in order to hide the memory latency. So if you have a warp that even one of my threads is waiting for memory, then I cannot proceed. So the warp scheduler will pick another warp that can proceed and put it on for execution. And then there is a small fast memory that acts like a level 1 cache, but the key difference is that it's also user managed. So you can essentially programmatically place data in that memory. Let's move on. So let's talk a bit about the execution model. So GPUs are like co-processors. So there's no OS running on the GPU. So the whole execution must be directed from the CPU. So the CPU sets up and launches what we call kernels. Kernel is essentially, you can view it programmatically as a function that will be invoked from the host and run on the GPU. And it's essentially the code executed on the GPU and the entry point to the GPU. That's called a kernel. And also the CPU has to manage the data. So the CPU has to copy the data that the kernels that will be launched on the GPU would need, and you have to do these allocations and transfers by yourself. So the CPU, not necessarily by yourself. That's what is called host-directed execution. Then there is what is called the unified memory model, where there is a unified virtual address memory space presented across the CPU and GPU. So that means that you can basically access a CPU address from the GPU, and then the software and the hardware will make sure that the corresponding page or pages are migrated onto the memory of the GPU, and vice versa. That really helps programmability, but it can come with some performance costs, and especially that in the past it was totally in the software, so it was really not very meaningful apart from just programmability. But since Pascal and the more recent architectures, they have hardware support, and also the drivers really helps on that. But again, it's something that can have some performance costs. So let's dive a bit deeper into the execution model. So as we said before, an application, the CPU launches the kernels, but if you see it from an application point of view, it's essentially your application that actually will launch the kernels to be executed on the CPU. Now we said there's so many threads that they can run on the GPU. So how this maps onto the programming model. So its kernel comprises several blocks of threads. So each thread can have up to a maximum amount of threads. And now each thread block can run on a single multiprocessor that I've just shown you a couple of slides before. Now, multiple of those blocks of threads can also be accommodated in a single SM, but there are some conditions on how many they can be. So since imagine that each thread has some requirements. For example, it needs some registers to run. It needs perhaps some shared memory, and there is also some hardware limits. So if you multiply that by the number of threads there in the block, then you compare that with, for example, your register file, then you can find out how many blocks can be actually accommodated. That's something happening by the hardware. It's not something that you manually do that. And now there's this notion of an active block, and that I'm going to explain more in the next slide, because here I will just confuse you more. So let's see how actually the execution happens. So here on the left are the blocks from the thread blocks from your application. So your application generates so many threads, and you pack them in this type of blocks. Now, on the right, we have the SM, where you have the warp schedulers, I've shown you before, the register file, and the shared memory. And let's assume that none of the blocks, your kernel does not use shared memory. Now what happens is that each block has a specific register usage, and that register usage comes from multiplying the register usage per thread by the number of threads in block. So here I can see that I can accommodate on my register file, for example, in each SM 4 blocks. So I will take 4 blocks from here. The hardware will take 4 blocks, the first 4 blocks, and we'll put them here, and the next 4 blocks, and we'll put them in the next SM, and so on. But let's assume we have just 2 SM. Now, notice the following. Those blocks are not scheduled for execution. They're not even put on any SM. They're just staying there. And in the CPU, they would also run those, because you had this context switch, but here you don't have. So the block, all the resources of the block, that's the registers of the block, are actually present on the register file. There is no way that the CPU is gonna take a block out from an SM, store its registers, bring another block in. That's not gonna happen. So a block stays on the SM for the lifetime of its execution, until it finishes its execution. Now, we have put blocks on the SM. These are called active blocks, which are the blocks that are actually can proceed with execution. Those are called inactive blocks. So now the warp scheduler sees which warps are ready to be to fetch instructions or to proceed with execution, and picks those and puts them actually on the SMs, on the course of the SM to run. So for example, here picks one warp from this one, then one from this one, then again one from this one, and then one from this one. Now, the warp scheduler, now if you see that if for example, this block, an instruction, a warp from this block is blocked in an operation, in a memory access operation, then the scheduler won't take this one. It will check from other warps, okay, which other warp blocks have warps that I can execute, and then we'll put them for execution. That's how GPU hides the latency. And then you see, similarly here, the warp scheduler will pick one warp from each from each block to run. Now, as soon as those finish the execution, then the next set of blocks will be put on the SMs, and then the kernel will proceed. Now, this has some implications. Okay, no, before going to the implications of that, one thing is about programmability. We said that each warp executes the same instruction. But what happens if somewhere in the middle of the warp, like in this case, we have a branch? Because as we shall see in Numba and in CUDA, you can essentially program per thread. So essentially you can say, if my thread ID is less than 4, then take that path. Otherwise, take the other path. Now, what's happening? Because the warp must execute the same instruction. So what's happening is essentially the threads. So let's start one by one. So we are at the condition. All the threads execute the condition. Now then we go to the next instruction. What happens here is that the threads that they belong to the next branch are basically deactivated. So the warp will execute the instruction A, the instruction B, but it will execute it in such a way so that the threads above 4 and above will just not execute it. And then we'll go to the next branch and we'll do exactly the same. We'll do essentially the opposite, so that the first 4 threads are deactivated. So the implication for that is that this can have performance penalty apparently, because the branches cannot execute in parallel, they execute serially. And this is called what we call warp divergence. Now, let's summarize all the implications from the execution model. First of all is we need lots of parallelism in order to cover execution latency. So we need to have, so the warp scheduler must have enough warps ready to schedule in order for the execution to proceed quickly. Because if not, if all of the warps are blocked, for example, memory, then it cannot move forward. Or if there's not enough parallelism exposed, then again, there are not enough warps to schedule. So if one is waiting for memory, then not enough things can be done. Now, there is one other implication that comes from, let's go a bit 2 slides before, from this fact that not all blocks are active at the same time, and the SEMs and the GPUs do not perform any type of context switching. So the implication of that is that I cannot have global synchronization within the kernel. So that means to synchronize all the threads of a GPU kernel across blocks. I can do that within a block. That's no problem, and we shall see that in practice. But we can't synchronize across all the blocks. And the reason for that is that if I had a barrier here, then it will just be a deadlock, because, for example, this block would not be able to proceed at all, because this one occupies the SM for execution. So I can't have a global synchronization. It would be really a deadlock. So that's something to keep in mind when you're, it's one of the biggest limitations that you have to keep in mind. It's not so big, because there's ways to work around this, and the standard way to work around this is that to launch multiple kernels. So if your application has phases where all the threads, you need a global barrier, then you should consider having spawning each phase of your application before and after the barrier as a different kernel, because you can synchronize outside the GPU. So then you can say in the CPU, you say, okay, wait until this kernel finishes. And then there's also other techniques that we're not going to see today, that you could even kind of streamline this several kernels with copy and and data transfers from CPU to GPUs so that you can hide communication latencies, but we're not going to cover this. So this is something that you need to keep in mind. Then another thing that's not common on, is not apparent on CPUs is this warp divergence, which essentially leads to redundant execution. You could argue here that this is quite similar if you, I mean, you don't see it on the CPUs at the higher level if you just look at your CPU at the thread level or the core level, but actually you can see it even if you're in your CPUs if you're looking at the SIMD level. So if you have a vector and you need to, based on the value of your SIMD vector, of the values you have in your SIMD vector, you need to execute different things, then again, it becomes quite similar. So you have to issue the CPU additional instructions to mask the different elements, which is quite similar to what happens in CPU. So essentially, you could see that the SM, the whole SM is like an equivalent of a CPU core, and each GPU core is more like a vector lane on the CPU. So yeah, that's about the execution model. Now let's move on a bit to the memory model. We haven't talked about memory at all. So there is inside the GPU, there are several levels of memory. First of all, we have the global memory, which is the equivalent of your main of the DRAM in the CPU. And in recent architectures from Pascal architecture and above, it's special technology called also high bandwidth memory, which is a technology actually that it stacks the way it's constructed, and it allows you to have to deliver very high bandwidth, and it's becoming like the norm for high performance now also on the CPU. So this memory delivers on P100, the GPUs we have on Pittstain 732 gigabytes per second. So just for comparison, the effective memory bandwidth for the CPUs that we have on date is around on 50 gigabytes per second per socket. So you can see the difference. Now this has even in the recent generations, this has exceeded the 1 terabyte per second. So we're talking about really big numbers. Now the key properties of the global the global main memory is that it is accessible from all the thread blocks. So it is accessible from the whole GPU. It's visible from everybody. One other feature is that the data that is there is persistent across kernel invocation. That's very useful because otherwise you couldn't hide the latency cost of data transfers between CPU and GPU. So usually when you're at the beginning of your application, you want to copy over all your data onto the CPU and leave it there as much time as possible, and they use it as much as you can, because then you have to pay the cost of the data transfers, which we're going to see how big it is. Now, one other feature is that the way the main memory is organized allows accesses from different threads inside a warp to be serviced with fewer transactions. That's called memory coalescing. Essentially, what it means is that if all the threads in a warp access addresses in a specific memory segment, because the memory is organized in segments in GPU, then in order to fetch the data for all the threads, all you will need is just 1 or 2 memory transactions, depending on the size of the types you use, instead of 32 transactions. That's a huge difference in performance, and we're going to see that in practice. And it's something that when programming for the GPUs is one of the, is probably one of the top priorities in optimizing and in looking when you're looking for optimization opportunities. Then there is a level 1 cache or shared memory that we've seen that before in the diagram about the SM. It's part of the SM and it is shared across the SM, which practically means it's shared among the threads of a single thread block. So a single thread block can access or write data there. One thing, this is quite fast. It has 1 cycle latency if all the threads of the warp access different locations, different memory banks. And one cool thing about it is that it can be either software or hardware managed. In the past, it was only software managed, so the programmer had to bring data into the shared memory and do the whole memory management. Now it can also act like level 1 cache. So it really depends how you program this. Now, one thing about caches and generally the execution, the memory on the CPU, on the GPU is that there is no coherency between the different shared memory. So as I mentioned before, that on the CPU, you have your cache that is shared across different cores. And if one core writes a memory location, and that memory location is cached in the shared cache, and then this change is communicated into the other caches of other cores. So when when another core wants to read from that memory location, then it will see that it has not an up-to-date copy in its cache. So then it will have either to go to a higher level of cache to get it. So that's a coherency protocol that the CPUs employ in order to make it easier to program. On the GPUs, there is no such thing. So it's completely left onto the programmer. Then there is also there's a very weak consistency memory model. So you can just reason in sequential consistency way, so that you can say that I have 2 threads, so their instructions will just be interleaved, and then I can somehow reason about the code. No, so you don't have these amenities. On the other hand, you have synchronization primitives, and thread fences and memory fences, which essentially you can put in your program a barrier, for example, and say, essentially instruct the hardware to tell it, now, as soon as you see that instructions, all memory operations before that must be completed. And then for example, that when you write in the shared memory, then for example, that write after the barrier is guaranteed to be visible. We're going to see that also in the practical examples. But it's something you need to keep in mind, especially if you use shared memory. You need to care by yourself for memory consistency. Now, there's also some other types of memory. One that is called local memory. That's essentially part of the global memory, and it is used by the compiler for register spilling. So when you compile your kernel and you make an excessive use of registers, then the compiler might decide to spill some registers onto that memory. So it's something that it's not visible to the programmer, but it's something that usually it can lead to performance degradations. And usually you can just see the produced assembly to see whether there's such type of accesses or there's registers spilled. Another thing is what is called the constant memory. That's practically, again, a part of main memory that is also cached. So separately, let's say cached. So there, the intention for that is to put their constants and make them cached. And then there is what is called texture or surface memory. And again, this is part of the global memory that is discussed and is suitable for 2D or 3D accesses. So imagine having a point which has X, Y, Z, then perhaps texture memory is something that you could consider. So practically the last two, the constant and texture memory, you see they come from the legacy or the original purpose of GPUs, which were to render graphics, where you have textures, you have points, you have geometry and things like that. So, but you can leverage and take advantage of those even for high performance computing. So how you program this? So first of all, there's the low-level native APIs like CUDA for NVIDIA GPUs, ROC for AMD GPUs, which basically give you the full control, but they're much more explicit. So in the ways you're writing your program. So a simple, I would say, kernel would require you several, like if you want to simply just a simple vector addition kernel or something like that, you have to set up your host vectors, copy them explicitly to the device, set up the block, the grid, send them over, copy back. So it's really very explicit. So you really need lots of boilerplate code. And that's why there's lots of effort going on since years about higher level approaches. One is using directives like OpenNP, and from OpenNP 4.5 there's accelerator support, or OpenACC. So so there actually you annotate your code or put pragmas in your code and say, now move that array over to GPU, or execute this loop in parallel on GPU and take care also of the data transfer. So it's much more let's say much less verbose, but again you have less control. Then one other interesting approach is higher level libraries written in, for example, C++, and then we expose interfaces to other languages, such as Cocos, Cycle, and these kind of things, which is essentially they try to blend into the latest C++ standards and about parallelism, parallel algorithms, etc. And behind the scenes, they essentially use CUDA, ROC, or whatever to manipulate the data and run kernels on the GPU. But that's not the purpose of this course, I know. We are in Python, which is another way. So, and you will see today that there's lots of work being done there. So you've seen before Numba. Now we're going to see today the CUDA version, the CUDA part of Numba. So there you can see from Python, you will see how you essentially generate CUDA code, and how essentially all the concepts I've shown here are exposed there. That's quite cool. And then we're going to see also CuPy in the afternoon. And there's also other like PyCUDA, PyOpenCL, and others. So there's a proliferation of high-level languages and libraries. So that basically concludes my morning presentation. So I'm happy to get any questions. If you have, just raise your hand and I will unmute you. I see quite of a silence. Okay, so I don't know if there's no other question. I think we could take the break now and then resume like, is it 10 or 15 minutes a break? Is it, Tim?
15 minutes.
15. So we can resume at 5 past, oh, we can say no, 10 past.
10 past,
10.
yeah.
10 past 10. Okay, so see you after the break. Okay, welcome back. I see you're all there apparently. Let's move now to the fun part. Let me share my screen. Okay. I will perhaps move that here so that, no, here is better. Okay. So we're gonna do the hands-on and present the Numba GPU, Numba for GPUs. Now, where you can find this is in Python HPC in Numba under Numba CUDA. So just click on the first and then let me know if you're if you're fine. And we're going to use the Miniconda Python HPC kernel. Wait a second. Just I need to see.
We just have a few people that are logging in at the moment, so just give a couple of minutes for everyone to get up to date. What
I need is participants. Okay, just here. Good.
Let us know in the chat box if you have any issues starting your notebook. I think everyone who is attempting to run is probably running. Also wave your hand maybe if it's, give a thumbs up if it's ready.
Okay, we have several people. This is thumbs up or just questions?
Or hands up or, yeah, hands up. Okay, I don't see any questions, so probably no one is struggling.
Okay.
So maybe you can get going.
Okay, so so generally, just to give you an idea of the structure, so there is also text in there. Obviously, I'm not going to read it. Is just for you as a later reference. And one key thing with Numba CUDA, for GPUs is essentially one-to-one mapping with CUDA. So if you have already programmed with CUDA, you will find it much easier. If not, you should do the, I will try to give you also the correlations with the concepts I presented before. Now, in the next almost 2 hours, my plan is that we cover several aspects. And we will try by writing a GPU kernel, moving data to and from GPU, spawning the GPU kernel, which is the essential part, let's say. Then we're going to see how we can profile. Oh, the screen is black. So my screen is black. Okay. I don't know if can you see now?
Louise, do you mean that your browser is or the presentation is? Because I can see the presentation.
It's not, yeah, currently it's not the presentation, it's a Jupyter, right? You all see the Jupyter notebook.
Yeah, I see the notebook.
Is anybody
Feel free to unmute your mic if you want, Louise, to clarify. Can't see, but can you see your own notebook, or is that the problem, or is it the slide presentation that you can't, the notebook presentation that you can't see. Can't see the presenter's notebook.
Okay, I can stop sharing and reshare if that would help. Okay, I am stop sharing then. And I will share again. Can you see it now? Can you see it? Okay, perfect. Okay. So I was saying that as soon as we write our kernel and we're gonna spawn it, then we're gonna see how we can profile a GPU kernel written in Python, in Numba CUDA. And we're gonna talk a bit about optimizing memory access. And we're gonna show us an example of how you can use the shared memory. We're not gonna cover CUDA streams. I not even just very quickly mentioned them in my initial presentation. So we're not gonna cover them here. So first of all, everybody needs to verify that everything is set up correctly. So just execute this. Numba -s will give you information about the system. So theoretically, if you scroll a bit down, you should be able to see, yeah, CUDA driver version, something like that. Okay, here, found one CUDA device. If you don't see that, just write in the chat. So here you see it's verify your Numba installation. Yeah, I think Rafael is more expert on that. If you have general problems and questions, if you have tried at home and didn't work. Okay, let's write our first kernel, which will be an easy one. So it's gonna be a vector addition kernel. And let's go step by step in the kernel. First of all, we need to import numba.cuda. And then very similarly to Numba, we need to decorate the kernel with the CUDA JIT or numba-cuda.jit. Now, this function here is a GPU kernel, and it has a complete analogy to a CUDA kernel. So what does this mean? So this means that this function should not return a value. And the reason behind that is that CUDA kernels are void functions in CUDA. So one other thing is this strange thing here, iCUDA.grid.1. We're going to explain it in a moment. What happens is that, as I said before, your kernel specifies what a thread will execute, a single thread, what a single thread will execute. So what is inside the kernel is what a single thread is going to execute. Now, remember that we have such huge parallelism in the GPU. Normally, this loop, you would write it on this kernel on the CPU, you would write it with a loop. You would say for I 0 to the size of the arrays, do the addition, or then you could just split this essentially to chunks. So for I to the first, from 0 to the end of the first chunk, and then for the second thread takes another chunk, and so on and so forth. Now here on GPU you have so much parallelism, and you can use even way more threads than your actual cores, as we've seen. So essentially, you should think of parallelism even at the finest level. So here, every iteration of that loop of doing the vector addition is independent. So I can have just thread just doing the addition of one single element. And that's exactly what this kernel does. And this is a difference in the mentality between CPU and GPU. So usually in the CPUs, we tend to think in loops. Here we should, the loop is happening a level above us, outside the kernel, essentially. So we see here, we need to start thinking about actual parallelism. So in this case, every thread executes just a single iteration of the loop that does the vector addition. Now, the question is, how can I get which element to compute? And this is exactly what this line here, this CUDA grid.1 does. Now, I forgot to mention that all the arrays that they are accepted by the CUDA kernel are essentially NumPy arrays, and NumPy array-like, let's say. We're going to see more in detail later on. So then you can take the shape, and then you say, if I'm beyond the limit, then I just return. Now, let's see how the threads are organized. And here it is. So you remember that a kernel is split into blocks. So into blocks of threads. So here, for simplicity, we have 3 blocks, for example, and then with 8 threads. So your threads of your application are essentially numbered sequentially inside the block. And then the blocks are again numbered as well. So you have block 0 with 8 threads, then block 1 with another 8 threads, and so on. Now, you need essentially to map this structure over your vector elements. And what you could do is, given your block size, which you know, it's a known of the program, we'll see later, and your position inside the block, then you could find your position in the whole array. So then you know which element to compute. That's essentially this computation, which you could write more explicitly in Numba CUDA as that. So could get me the block ID, the block ID, which is the block 0, block 1, block 2, multiply that by the block dimension, so this factor, and then my thread ID inside the block, and then I have my absolute position. This is a very, very common operation in CUDA kernels. You always have to do some type of that operation. So for that reason, there is, Numba offers this convenience function, which says, okay, give me the absolute ID given that I have a one-dimensional grid, and it will give you the absolute position. So this is not part of CUDA, it's just convenience from Numba, and I think also OpenCL had a similar thing. And generally, whatever is higher level, usually they need to provide, they usually provide such a thing because it's very, very, very common. Now, next as I said, we take the shape of the array. We just have an if there that we mask out the threads that have to do work outside the array boundaries. And then it's the actual sum. Now, it's not enough because—
Can I ask a question?
Yes, please.
So CUDA.grid 1, what's the meaning of the input variable 1?
The
number of dimensions, what's the meaning of number of dimensions?
Yeah, forgot to mention that. Yeah, you say that you have one-dimensional blocks. So then it knows how to compute this. Because you can say I have two-dimensional blocks, and then this computation will be a bit more complex, and it will give you a tuple of your position.
So at that time, the input variable will be 2, kind of thing.
Yes, the grid here, you would be 2, if you had two-dimensional blocks. But we're using one-dimensional. But I don't know if I get it correctly what you want to ask.
Okay. But you have to, I mean, you have to define the block size or.
Yes, we're going to see that later, how we invoke. Yeah, you define the block size in order to invoke the kernel. We're going to see that in a moment.
Okay, thank you.
You're welcome. So now the kernels, both in CUDA and in Numba CUDA, they operate on data and on arrays that they actually are on the GPU. So they can't operate on arrays that they reside on the CPU. Okay, I mentioned before that there is this unified memory model, but it's not the norm. So the arguments here of X, Y, Z, they should reside on the GPU. So so far we haven't done anything about that. And now this is the time to do it. So first of all, we create our NumPy arrays. I have a small size here. And we compute our reference result. And then now we want to copy those arrays X and Y that we have on the CPU to the device. So there is this convenience function CUDA to device, where you take your NumPy array, and then it gives you back a NumPy array-like object that has the shape and all the look and feel, but whose actual memory resides on the GPU. So this is what we do here. And essentially we are copying over to the device. And you can verify that you see that's a Numba CUDA DRV device array, blah, blah, blah. Now, we need to do the same for the Z. Now the Z, it's not something that we need to allocate on the CPU, because it's just the output array. So we don't need to create a NumPy array also on the CPU for Z. We just need to create directly on the device, and that's how you can allocate an array on the device. Since it's an array like X, so the same shape, same type of elements, so we can use the CUDA.device array like X, and then we create the Z array here. Now, let's invoke the kernel. As Jordan said before, how we specify the block. Actually, now it's the time that we need to specify the block size. So I said before in the introduction that its kernel comprises blocks of threads, and your application comprises several blocks. So each block comprises a set of threads, and your application comprises a set of blocks. Now this set of blocks is called the grid. So when you invoke a kernel, you need, as a programmer, to specify both the blocks and the grid. So in this case, we're using one-dimensional blocks with a block size of 128. And our grid size, which is the number of blocks essentially, is the number of elements we have in the array divided by the block size and taking the ceiling. So now the question is, why block size 128 and not another number? Okay, one first thing is that you remember that execution happens in blocks of 32 threads that they execute the same thing. So having a block size less than 32 is a bit silly, because essentially you have half-empty warps. Now, why I chose 128 is just a good guess. There's no, I mean, the block size affects the occupancy and then a bit the performance, but it's not the decisive factor of performance of a GPU kernel. So any number, it's usually the final fine-tuning after you fixed all other problems you had with performance. So generally from 64 to 256 are usually going to give you some good performance, and then you just fine tune it. So here I used 128 which is quite common. It's also, for example, the default that is used in, for example, in PGI OpenACC implementation, they use by default a thread block of 128. Now, as I said, we did the block, we compute the grid, and now it's time to invoke the kernel. And you have to do this syntax here. So your Python function name, and then you pass this square bracket syntax with a number of blocks, that is the grid size, and the block size. This can also be tuples in case you have two-dimensional blocks, and correspondingly two-dimensional grids, and then you pass your device arrays. Now when to use two-dimensional grids and two-dimensional blocks, that really depends on the application, and they're just there for convenience to do an easier mapping of the CUDA threads over to your problem. So in our exams, we're just going to, in our all exams, we're gonna use one-dimensional blocks and grids because it's also more convenient and easier to understand the reason about. So let's call our kernel. Okay, now we have run our kernel on the GPU. Now let's, I think you can also do this cool thing here, GPU utilization, just to verify, although it's very, let's see, the GPU memory. Okay, so you see, okay, the arrays are very small. We can just, we will keep it open just to, okay, I'm gonna do that and see. Okay, we'll increase the arrays later on. So now the kernel has been logged, has finished, and now we need to copy back the result. So so then we can use this copy to host from a Numba CUDA array that resides on the device, copy to host, and that will create a NumPy array with the same shape, etc., array elements on the host. And now let's verify that what we computed is actually the same to the reference, to the NumPy. So here I have put everything together so as to have an idea. And that actually concludes our first notebook. And now there is a couple of exercises that we're gonna discuss. So I'm gonna let you try, just try now increasing the host vectors. Okay, I've done that, but perhaps I need to make a bit larger the hope you can still see my notebook, right? And I'm gonna do also this guy here. Okay, so yeah, just play a bit with the vector. Let's see again. Let's see if we, this is really small. So, okay, let's increase the vectors 1,000 more. Are we done here? Okay, I will try again. I haven't used a lot this GPU panels, but okay, but we're gonna do something else. So I'm gonna increase it to 200 million elements, which is several. Okay, now you see that I've copied to the GPU. So it's about 4 gigs, yes. Is it finished? Yeah, it has finished. I'm gonna see also the GPU utilization here. If it, So you see the kernel launch on the GPU. Now, let's do the following. Let's take step by step. Let's time it, right? You know, time it will, I want to avoid the effects of time it. We will iteratively time statement. So I'm gonna do one iteration and just time it once because I want to take just this time. Okay, let's see. Okay, 223 milliseconds. Let's do it again. Now, let's increase the repeats. Okay, so that's something here, right? So it says that your first run was like several milliseconds. The second one was much less. And then the average is in the order of milliseconds. Let me increase the repetitions. Okay, so you see, so again, I mean, something's happening here. So the first time I run the kernel, it's way slower than the rest of the times. But the question is, why this is happening? Is it something related to CUDA or is it something related to Numba? So the answer is in the next notebook, which you can find here. So it's called the performance analysis. So you can switch to that. And now one thing you will need to do is you should shut down the kernel from the previous notebook, because it kind of holds the GPU. So if you try to run another GPU kernel from another notebook, then you might get an error. So now what I'm doing is I shut down the kernel. So what is happening is that you remember also from the CUDA, from the Numba lesson, that Numba uses just-in-time compilation. So because by default, Python has no, it's a dynamically typed language, so it's not statically typed. So you don't know actually the type of your arrays before the runtime. So before you call it. So the problem here is that Numba CUDA waits for the runtime, sees that I have double arrays here without save, and then it compiles the kernel. The first time you do that, it will compile the kernel. So then you will have been counting also the JIT cost, and then it will just invoke that kernel. Now the problem with Numba CUDA is that there's no cache parameter that you can pass to the Numba CUDA JIT. Because, no, I don't know the reason, but this is a fact. And so then you can't basically ask Numba to cache previously generated kernels and then avoid the JIT cost in subsequent invocations. But what you can do though is what we're gonna do in this notebook. You can pass a signature of the array of the function to be generated, and then Numba will essentially compile that code at the time it executes the decorator, which is at the import time, which is at the time the function is defined. So before your function is called. So let's see the syntax. So here you say, I have a function returning void, and your taking arguments, array is a NumPy array, so it will generated the actual type for C that uses double. It's one-dimensional, and it has row major order, so the C conversion, not the Fortran. You could put here Fortran if you wanted the Fortran conversion. And then 1, 2, 3 arrays. You can't specify whether the array is input or output, or I don't remember such thing. So perhaps, but I think he can guess it also from an analysis. He's doing already an analysis. He can easily guess whether an array is input in or out. So generate an optimized function code. So then the kernel is as we have. So let's execute that. So notice here that it's still executing this thing. Why? I think it takes a bit too long.
It looks like you're not connected to the actual kernel, the Jupyter kernel.
Unless no
So
kernel, yeah, no
top,
kernel, yeah. Okay, so I had no kernel, yeah, good. Okay. You see, it takes some time because actually it compiles. Now, let's now time again, right? Let's again, we have our big vectors. And I'm gonna again time it. So now you see it's at the order of microseconds, and we were at milliseconds. Okay, but I will try to decrease the array size. Okay, 187. Okay, let's do 100, 211, and again we had 190. What is happening? So I'm timing the kernel, and I mean, those GPUs are magic. So they execute the code so fast, regardless of the array size. Well, actually, that's not true, and it couldn't be. We wish it would, but it's not. So actually, what is happening is that we're not measuring the kernel time. We're only measuring the kernel launch time. And that's why it's almost constant at around 200 microseconds. And the reason is that in CUDA, kernels are launched asynchronously. So when you launch a kernel, the kernel just, you send that work over to the GPU, and then the CPU calling thread continues. So this is exactly what is happening here. So we spawn the kernel, and then the CPU proceeds here, and it blocks. And there it blocks until the actual computation finishes on the GPU and copies back. Now, if I want to be more precise, this is when you spawn a kernel, it actually, CUDA GPU has some what they are called CUDA streams, or let's say work queues. You can imagine as work queues where you push work to be done on the GPU. Now, what this work is can be either a kernel, a kernel launch, or not a kernel launch, a kernel, or data transfers. So here, what we're doing is essentially pushing to the default work queue or to the default stream a kernel to be executed. And then later on, again, we're pushing a copy operation from the host device in the same work queue. Now, all the things that they are in the work queues execute serially. And here I'm just blocking until the work in that work queue finishes so that I can get my result back. That's the technical part of why it is blocking here. But essentially, it's not what we want, right? We want to measure the actual execution time of the kernel. So now, unfortunately, we can't do that with time it, or I couldn't do it. I mean, there might be a way. I'm not so good into the Jupyter details. So we're going to write our own timing function, which is essentially, we're going to use a context manager. If you haven't seen context manager, it's a good example where you can just go here and understand how it's called. So the idea is that we want, like, with time region, and then whatever is inside this with time statement, we measure it. So essentially what we do is we call time, and when we enter the region, and again, when we exit, and we have this function here that we can then get the elapsed time. So let's do that. So here again, we have the same, we call the kernel, but with this thing inside our time region. And then we're going to print the time. Okay, there it is. Yeah, I didn't execute this one. Okay, again, you see 236 microseconds. So again, we're getting the same more or less time we were getting with time it. Now, but again, now that what we know is just that our time region is correct, our timer. Again, 194 microseconds. But we want to measure the kernel. Now, there one way to do that. So you remember I told you that there is, when I was talking about the global barrier inside the GPU and saying that it's not possible to synchronize all the threads, but you can synchronize at kernel level, this is exactly what we're going to do here. So we're gonna say on the CPU, say, okay, now wait until the kernel is finished, like a global barrier on the CPU side, waiting for the kernel to finish. And essentially, this is you can achieve that with this CUDA.synchronize, which this is a bit like it's like a bit of a hammer, this operation, because essentially you're waiting for every operation on the GPU to finish. So for I talked about work queues. So here you wait for all the work queues that they're doing some work on the GPU to finish their operations. So it's a really bulk thing, a bulk weapon, let's say. So, but now we'll stop there, and then we can measure our kernel time. Okay, let's do that. Okay, and I'm printing also some times. 0. Why NumPy is so? So now we're getting, you see, for the CUDA kernel time, we're getting 9.4 milliseconds. So apparently we're not measuring the kernel launch time. We'll run again. Because why NumPy is so, let me just open my, yeah. So now notice that now we have a comparison between the NumPy addition time and the kernel, and it's about 15x faster. We're gonna see whether this is good or bad later on. For the moment, let's work around. Let's find. I want to introduce another way for instead of CUDA synchronize, because CUDA synchronize is not something that you, as I said, you will have to do like in. You might not want to do it all the time. So I talked a bit about the work queues or the CUDA streams. Now there is one thing that you can put in those work queues, and this is called an event or a CUDA event. Now imagine of an event like a milestone. So when it is processed, it basically raises, when it's processed in the work queue, it raises like a flag that I reached that milestone. And then when you put another event, again, it raises that milestone and so on and so forth. And that's a way that we can measure the execution time of individual operations. And it's also more precise than just measuring from the CPU side. That's what I'm saying here is also both valid for CUDA and for Numba CUDA. It's exactly the same. So what we're gonna do here is we're gonna place an event basically in the stream we're running, which is the default, just before the kernel and just after. So then we can measure the time. And here is this version of time region context manager that actually uses CUDA timings. So I'm not going to go through all the details. You can find them also in the documentation. So essentially, we need first to create an event, which is this CUDA event, and you should set timing to true. Also for the end, because it's not like a timer that you have a timer and then you take another one and you update as we did before. You have to have two separate events for the beginning and end of the operation you want to type. So essentially, when we enter the with statement, the region, then we start recording. So you call the record method on the tstart CUDA event, and when we exit, we call the record method, and then again synchronize on the event. And then elapsed time, there is also an event elapsed time here that you pass two events, and then it counts time in between, and this is what we wanted. I think it gives you the time in milliseconds. That's why I'm using this conversion factor here. And yeah, ignore the time offset. It was just something for implementation specific. I don't remember what I wanted to try. Anyway, so let's do that. So again, we have time region CUDA. And now we don't have CUDA synchronized. Yeah, yes, of course, because I didn't run this. And then okay, so you see again, the times are correct, as we've said with our time region, but we don't have the CUDA synchronized. So here, for example, we could have other operations running on the GPU concurrently, and we wouldn't have to wait until all of those have finished. So that's very handy if you're using multiple streams in your application. You want to measure different parts of the string. That's where it is quite useful. Now, let's come to the question and see. Okay, we've obtained some performance, and now we need to understand whether this is good or this is bad. But before doing that, we need to look a bit more into our algorithm. And our kernel is here. I'm going a bit. Okay, I need to go to scroll up.
There's a question.
Yes. Where is the question? Here. Shouldn't we? I will answer live. So yes, good question, and we will do. I have that later on. We will see that. So so let me repeat the question because I don't know if it was. So shouldn't we measure the time spent in data moved from host to device and vice versa? Yes, and this is what we're gonna do later on, either in this notebook. I think yeah, later in this notebook.
I'm sorry, may I join in with a short question?
Yes.
When I reset the kernel and execute the first cell, I noticed in the GPU memory that around 300 megabytes are reserved. Why is that?
So you mean this cell, the first one?
Yeah, the very first one, if you reset the kernel and check the GPU memory. you see that just for the compilation, you have 300 megabytes reserved. Do you have any idea why that is the case?
This I really don't know. Yeah, I see them. I see now. Now I have data in my case, so it's 5 gigs. But this I don't know why it uses. I really don't know. I haven't looked into that before.
Okay, thank you very much.
Okay, so before going into the data transfers, I want you to understand whether the performance we're getting for the kernel is good, bad, average. So to do that, we first need to see the code. So essentially, what we do here. So when you want to analyze the performance, there are basically 2 things you need to look at. One is how many floating point operations you're doing for your whole kernel, and how many data you need to transfer to or from the main memory. So let's do that thing here. So essentially, we have just one floating point operation, and we do that for each of the elements. So so essentially, we have n floating point operations, and we need to transfer read n double elements, 2 n double elements, and write n double elements. So in total, we need to transfer 3 n double elements, which essentially gets us back to the discussion here that for each floating point operation, we need to transfer back and forth from the main memory 24 bytes. And that gives us a ratio, what is called float per byte ratio, or arithmetic intensity of 0.0417. Now, you don't need to know if this is high or bad, but apparently it seems very, very low, because you need to transfer so many data just to do a sync floating point operation, which is not ideal. And in fact, it is very, very low. So essentially, we expect that this kernel should be bound by memory bandwidth bound. So we can't exceed the available memory bandwidth bound. Now, the question is, the answer to the question whether we perform well or not is how close the memory bandwidth to the effective memory bandwidth of our target architecture we are. So this is essentially what we're going to compute in a high-level way here. Now that's for the GPU. So I have computed also the performance. So you see it's 21 gigaflops. That's ridiculously low. So I mean, you're getting like teraflops or hundreds of gigaflops. I think it's in the order of teraflops even on the Pascal. And then we have the transfer rate, which is 519 gigabytes per second. We're going to back into that in a moment. And on the CPU, again, more or less the same motif, 1.3 gigaflops per second, very, very low performance. Transfer rate 33 gigabytes per second. Now, recall from my presentation before that the maximum memory bandwidth, the nominal memory bandwidth from the GPUs were 732 gigabytes per second. And here, here we're getting just 519. It's high, but not that high. Well, I mean, in reality, it's almost the max we can get, because not all of the bandwidth, the nominal bandwidth, is achievable. In fact, if you do benchmarks, and if you even measure with performance counter for NVProf, you will see that usually the maximum you can attain in this type of GPU is 550 gigabytes per second, which brings us very close. So essentially we have 520, and we can't, practically meaning we can't get more performance because we hit the memory bandwidth and our algorithm has no more capacity. Now for the CPU, again, I mean, in the CPU, when I've seen that number, it wasn't as much as expected. I would expect around 50. And I investigated a bit why we're getting 33, and the reason for that is that for some reason that needs to be investigated, its NumPy version doesn't use the whole CPU. It just uses 12 cores, 12 threads, but essentially uses hyper threads instead of spreading them across each individual core. And I think it was yesterday, perhaps Theo, that showed you that, for example, with Numba, then you could even get this extra performance compared to NumPy in one of his triad benchmarks. So I'm not going to go into why the CPU, but generally we've seen that the performance we finally got with our kernel, which is written in Python and then translated to CUDA, is basically native performance. We can't get more. If you write the same kernel in CUDA, you wouldn't get more. And we proved that here. Now, so let's move on. And then we're going to address the big question of, which was from, I don't remember who it was, about the data transfers. Now, we measured the kernel. Okay, the kernel will 10x faster from the CPU, and that's quite cool. But it's, unfortunately, we have to transfer stuff. And here is what we're gonna measure. So first you notice here how I use again the my timer with the CUDA events. So you can use that for any CUDA related activity. So then we're using CUDA to device, and then we're essentially measuring the time of those copies. And then we do the same for the creation as well here. And we use this for the kernel, and we use for the copy back. Now let's see. Okay. So now so CUDA kernel time, 9.2 milliseconds. NumPy time as before. Now copy in time, 0.4 seconds. So if we add the copy in time, the creation time, notice that this is also significant. The copy out time, we're like 8x slower on the GPU. And that's something that it's one of the messages you need to take when you're working with the GPUs. Data transfers between the CPU and the GPU are really can really become bottlenecks. So make sure if you're working. I mean, now this is just a kernel. We can't avoid it. But if you have a bigger application, you should make sure to copy all your data you will need along the way as early as possible on the GPU and let it there as much as possible. And if you can't do that, you need, because your data set is very large and you need to transfer in and out, then you should certainly investigate techniques that would overlap this communication, this transfer, and of actual computation using CUDA streams. We're not going to cover this, but it's something that you really need to keep in mind. Now, we're going to see, though, some tricks to accelerate the transfers themselves. First of all, let's measure how the transfer rate. Copying rate, 7.9 gigabytes per second. That's not bad, given we have a PCI 16x bus. I think usually the maximum you can get is no more than 8 point something for this type of memory allocation. 8 to 9. Oh, copy back, 2 gigabytes per second. That's certainly bad. That's really bad. So what is happening here? Now, when you allocate, that relates on how the memory is allocated and how much the operating system intervenes. So when you allocate memory, this memory is on the host is by default pageable. That means that if the operating system needs to it needs to get this if the operating system is low on memory and it needs to swap out some memory, then it can take that memory region and swap it out that's been putting on the disk. But in order to do that, it has to maintain some mappings in its page tables and also know whether a page resides in memory or not. So that's also true if the memory is regardless of if the memory is going to be paged out or not. But so when you write to a memory location, as we do here, so here we write essentially to the memory at the host side. Now we have allocated the memory, but the OS, when you allocate the memory, it doesn't actually reserve physical memory. It just, for the operating system, it's just a mapping and saying, okay, this region belongs to you. I'm not going to give you physical pages if you don't request them, because I just want to make sure that I can serve other people running on the operating system or other processes. But as soon as you start writing, then the operating system will try to say, okay, this guy writes on this. Do I have that page in memory, mapped in memory? Oh no. Then it goes through the hardware, gets an interrupt, back to the OS, and the OS allocates a page for you, and then gives back control to the process, and the process writes onto that memory. And this happens for every page that is being missed and is faulted. So that's why when you write on the page here, it's quite slow, because it's not the PCI. Now here you're bound from the OS essentially, and not from the PCI Express transfer. Now there is a way to work around this, and these are called pinned arrays. So a pinned array is a memory region that actually you mark it specially so that the operating system will physically allocate that to you when you do the allocation, and it will not move it or page it out or swap it out on the disk. So it will always reside in the physical memory. So then there's no interventions of page table translations and things like that, or OS interventions. And that could really speed up things. And these are called pinned arrays. But as you might imagine, they come with a cost, because actually you're reserving a space in main memory, so you can really go, you can cause problems to the rest of to other applications, or to your application basically running if you have high demands, because you have a dedicated space buffer for these transfers. And it can also lead to perhaps segregation, and the OS cannot get large contiguous amount of memories when you ask for an allocation. So it comes with at this cost. Now we're going to do that to show you the difference. So now I'm going to allocate the result using this array. So first I need to allocate that array, and you do that with this CUDA pinned array. And again, the nice thing about it is that all these arrays are NumPy array-like. That's a nice thing with CUDA, with Numba, sorry. So I'm creating that, and then I'm copying to that pinned array. And look at the transfer date. So now we're at 13 gigabytes per second, we could even get to this performance also for the copying, if we want to make to pin the arrays also there. I leave that as an exercise, and I'm not going to do that now, because we have to finish that notebook and then we have another one. Now, one thing you will need to do is, for example, profile Dismiss. Am I? Okay, sorry. My time expired. I have a question. Okay. So I think, Tim, I think we have a problem. It seems that that in other users, in other attendees.
Yeah, I'm just having a little look.
Yeah.
Looks like maybe just wait for a few minutes and we'll see if there's a generic problem on the machine. Looks like Daint might be running a bit slow at the moment.
It also appears in my computer.
Oh.
Okay, it looks like the system administrators are aware of the issue that we currently have on the machine. So hopefully we'll be back in a couple of minutes.
Yeah, we can, yeah.
Okay, there was a problem. There's a problem with the scheduler. So Slurm has crashed at the moment. So maybe we take 5 minutes break and then come back, Vasilius, or if you want to continue. It's up to you.
Okay, I could continue a bit just describing. It's not something here that you need to run, so I could continue. It's a bit annoying though, this thing.
Okay, so we might we might be back.
Yeah.
Can you try relaunching?
Okay. Yeah. Okay, start.
Just give it a few minutes for the system to recover. Okay, most of the jobs should now be going into the close to the run stage. So you should be up and running,
Okay.
hopefully within a minute or less. My one has just started, so
Okay, mine is this
could
one.
be quite close to running.
Oh, yeah, it's not the right one. Sorry. I was here. Okay. And let's put also the GPU. Right. This as well. Okay, let me close this. So I'm unmuted. Okay. So we did our analysis, performance analysis a bit manually, but usually when you have a more complex code or a code that you don't know, it's not always something that you can easily do right from the beginning. So that's why we have also different profilers. And I mean, we have profilers, and also NVIDIA provides basically two set of tools, let's say. The most recent one is the Nsight suite, which has two components, the Nsight systems and the Nsight compute. One is for general profiling the systems, and the compute is for detailed profiling inside the kernels. And we have also the older tools that also work with a bit older GPUs reliably, is NVProf, which is the command line profiler, both for more high level and for detailed analysis inside the kernel, and the visual profiler. So the nice thing is that since everything is CUDA translated to CUDA from Numba, then you can use those tools. I'm going to show you how you could do that. So in case you want to try, I need a new terminal, file new terminal. Okay, here. Oh, I want it here, basically. Okay, so first thing you need to source your, come on. If you want to profile first, you need to source the Python of the kernel. Okay. So that you have Numba, etc. And then you know to load the Nsight systems. That's for the general profiling. And you see, I'm on the compute node. Okay, let's go to. Okay. And now you can launch this. So essentially an NSYS profile, and I'm going to explain you right here. So here NSYS is the program to profile, and NSYS profile, you essentially profile, -o is the output. And now in this source vec.add.py is essentially the program I've just shown you in the notebook, but separate and with a main function. So it basically does the same thing. And I'm just going to launch that. Normally, if you're in a login, oh, what's the problem? Expected thrown. What is that? Yes, I think I should fix them. Yeah, I haven't pushed that change. This has to be an exec. Yeah, sorry, that's my bad. That's my bad. That's my bad. I forgot. Yeah, I should fix the notebook. So here I forgot the Python 3. And now, I mean, you see it runs on GPU and collects data. And then I'm going to switch to another window just to show you a bit how it looks like. There's also, as this runs, there is also one little thing that you have to do if in your code, usually to compile with NBprof, is you need to put this thing at the end of your code, because sometimes it might not let you, it can collect the data, but not dump it. So you have to put that statement. I want to show, on the other hand, we don't have such time for the, okay, processing. Meanwhile, I want to, okay, as I don't know why it takes so long, but meanwhile, I can stop sharing this window and want to share another one from a previous run, just to show you how it is. Okay. So here you must be viewing my NVIDIA Insight systems. Usually you go open and you find this QD rep file that we produced here. It remembers it from a previous time. Oh no, okay. Yes, of course, because I need to mount. Yeah. Okay, yeah, I needed to mount so here you get a full overview. So the nice thing with NSYS is that it shows you also what's happening on the OS. So here we even see the Python running, right? What's happening, OS runtime libraries here, for example, is opening the file of yeah, perhaps it's for compiling and so on. You can, that's pretty cool. And you have also what's happening on the GPU. And we can just focus just right here. And so here you see the CUPA MEMCPI. So you see the actual CUDA cores. And here you see the host device and of the two arrays. And there you see the copy back. And here you see also the allocation for the pinned array, QMEM host alloc. And look how expensive it is. But where is the kernel? So the kernel is really fast. So the kernel is this little thing here. Not even, so here. No, this is the this is the allocation of the Z array. Our kernel is still more tiny than that. Here is our kernel. So, yeah, and then you can see, the nice thing is that it is annotated. So then you can see which kernel, if you want to profile, so you know it's the Vega at line 241 in your, I hope it's, I don't know if you have so many lines, to be honest. It might be in the generated file. So I don't know how much this 241 corresponds to the actual Python source. I don't think it is, to be honest, but you know the kernel. And here you see some information, when it started, when it ended, the return value, also the stream, if you're using multiple streams. And generally you get like this high level information.
Vasilius, maybe just double check with show of hands whether people can access the interface, because there's a question.
Where they can access, okay, so.
If they can, because Hannes cannot.
So actually there yeah, I will answer that. So what's error when running the NSys command, even though I sourced the Miniconda? What type of error are you getting? No module named Numba. Oh, that's probably the wrong kernel that you sourced, but where is the thing?
Feel free to jump on live if you like.
Yeah, so actually, so you sourced this thing and you said you can't have Numba. You know, if it's
Yes, I sourced the exact same command, but maybe I'll try it again with another terminal.
Yeah, unless my kernel is named the same, but it's not the same. But I don't know if anybody from the panel, like I don't know who's there or team, if you can just after you source, just do this kind of if that gives an error or not, or think. So moving on, so we've seen that. The nice thing is that I've shown you the interface. So you can have this end-side GUI in your laptop. So you don't have to bother connecting with X, etc. Just get the file and open it there. That's very similar also with NVProf. Now, ideally, I wanted to use NVIDIA and SYS, which is the new way, and compute and site compute basically. But site compute doesn't work, doesn't support the detailed analysis that I wanted to do for Pascal GPUs. So one thing is, I've shown you an overview of an analysis, but then you might want to go into details of the performance. So how much memory bandwidth did my kernel use? Which are the instructions taking up the most of the time? How is my memory access pattern? And so on and so forth. So this, you need a more detailed analysis that will read some performance counters from the hardware and will rerun your kernel several times in order to collect them. And this you can achieve with this. So NVProf, the output file, analysis metrics, and then pass the command. Since I want to move also to the next notebook, you can do that. And then again, you can visualize the results through the NVIDIA Visual Profiler, which again, you can download and have it on your laptop and just import the NVProf output. And there you can see again the kernels, the memory moves, etc. And you can click on a kernel and you can click on analyze. And then there's several levels of analysis. And there you can see, so here in that screenshot, I have selected the memory bandwidth. And there you can see that the actual memory bandwidth measured from that run from the hardware counters is like 557 gigabytes per second. And you see it's highlighted in red because it's your performance limiting factor. So you can see really this type of information, but from the hardware perspective. So that concludes the analysis, the performance analysis part. Then we can move on. Since we have half an hour, we can move on to a third notebook. It's a bit more advanced topics here. And let's close this one. So here, we're going to expand our example and basically expand this. We had vector addition, so we're now going to implement a matrix vector multiplication in the GPU. Let's try step by step. So again, this is the boilerplate we had from previously. Perhaps I will need to shut down another kernel. Yes, shut down. Okay. Now let's see a bit the actual kernel. Here again, I'm doing the trick with the just-in-time compilation. So I'm using the same interface as plus. So we're computing the alpha by A by X plus beta by Y. Now again, I'm using one-dimensional grids, and I think it's better if I show you here. That's to visualize it. So we have our array. It's row major by default. So it's like that, the elements. Then we have our X vector, and then we have our output vector. So what we're going to do is we're going to assign a row computation to a thread. So T0 to T7 are the threads for demonstration purposes. So each thread, what it's going to do is going to compute the dot product of the first row and the X array, and then compute that and store it to X. So that's the most natural way to do it, because otherwise if you wanted to assign columns to threads, then it would be, you would need a reduction step, which is not so straightforward to do in GPUs. So let's see the kernel now. That's the key idea. And again, you see each kernel describes what a thread will do. So I'm getting first the position. Again, we have one-dimensional threads and one-dimensional blocks, sorry. And then we're getting our position, the usual stuff. So this is only for square matrices. We don't care about other types of matrices. It's just for demonstration purposes. And then we go through the columns, get actually the partial sum, the reduction, basically the dot product, and then we do the final operation and the sign. And I have also this wrapper Gemp GPU, which does also the data transfers. Again, I'm using a pinned array from the copy back, the block size, and here I'm calling the kernel as we've seen. Notice how you don't have to care about constants, or not constants, about scalars. So alpha and beta are scalars in Python code. Then you just pass them to the kernel, and then the kernel launch mechanism will just make sure to copy them over to the GPU. And then copy back and the usual stuff. And then let me just run it. Okay. So now we have a pretty small array. Now I'm going to increase it to more reasonable numbers. Well, I mean, big numbers. So let's say 16K, which is pretty large. Okay. Now let's see a bit the performance number. That's a quite large array. As you see, it's like several gigs. And before that, I forgot to say, we also compute the reference for NumPy. So we're using the operators for the matrix multiplication. And the idea is that we expect NumPy to optimize that and recognize that, which it does. And then the different operations. But let's see the times and the performance. So consumed bandwidth is in 139 gigabytes per second. And actually, this time, the code is not so much faster in the GPU compared to the NumPy. So it's like twice faster only, the kernel. So you see the kernel is 0.015 and the CPU is 0.37. Why is that? I mean, is the performance we're getting expected or not? What we would expect to get. So let's do again a bit of the analysis. So if you do the same analysis we did for the vector addition kernel, you will see that in total, we will have to transfer, first, we need to perform 2n squared plus 3n operations. Because if you go here, you will see that, yeah, we in the inner loop, we do 2 floating point operations, one addition, one multiplication. And we do that for the whole matrix, so 2n squared, assuming square matrices. And then we do 1, 2, 3 more operations n times for the final vector. So that's how we have 2n squared plus 3n operations. And at the same time, we need to transfer n squared elements of the input array, because we need to access them all. And then the x and y, to access the x and y arrays, which is 2n. So multiply that by n bytes. So if you do the math here, and if you assume that that n is sufficiently large, as in our case, then you end up that you have a float per byte ratio of about 0.25, which is again too low, which means that for each floating point operation, I need to bring 4 bytes, which is a lot. So again, we would expect to be memory bandwidth bound. I have here in the node what would be the float per bit ratio, so as not to be memory bandwidth bound. And it is much, much higher, as you might imagine. So nonetheless, we're getting 139, right? And the CPU bandwidth is, okay, you see CPU bandwidth is 56. Now, for that reason, yeah, I mean, it seems that NumPy got it correctly with the threads this time. This is for us to investigate. But nonetheless, I mean, on the CPU, we get the maximum. So the kernel has the capacity to consume the full memory bandwidth. On the GPU, though, we're just getting like 1/4 of what we could get. What is happening? Let's see a bit the access pattern. Let me see if I have it here. Okay, let's see a bit the access pattern, right? And let's see what each thread accesses. And imagine also not only what each thread accesses, but also what happens inside the warp. So each thread, what each thread does, each thread accesses X sequentially, and it accesses A, the array, sequentially, right? And the next thread does the same, and so on. That is ideal access pattern for the CPU, and we've seen that with the NumPy. The threads are accessing sequentially data, but it's not the case with a GPU. And with the GPU, the problem is the following. Recall from the discussion and the presentation in the morning that all the warps, all the threads in a warp execute the same instruction. So what does this mean? So here we have 8 threads, and let's assume our warp has only 8 threads, okay? So what this means is that all of us, we're going to execute a load instruction. But that load instruction, what is going to load? So we're all going to load X0, and this is pretty fine. It will be broadcast to everybody. And then, so then T0 will access this element. My neighbor thread will access the 8th element. The T2 will access the 16th element, and so forth. So what happens is that the threads of the warp, they access locations in memory that they're far away from each other. Although each thread accesses sequential locations, the threads inside the warp access locations far away. And that's really bad, because imagine, again, recollect the discussion about how memory transactions happen in GPU. So in GPU, it's what the memory sees are warp operations So now the warp would request 32 addresses that they are far away apart, and then the memory system will have cannot coalesce those into less transactions. So it will have to do 32 transactions to service that warp. And meaning that none of these threads of the warp can proceed, and the warp will be blocked until all those 32 transactions bring the memory, the requested memory. Ideally, what we want is to use only less transactions, and ideally we could use down to 4 transactions. I have a bit of analysis here why it's 4 transactions and not 2 or 1. It's just a hardware thing. So ideally, because we have floats, and then we could have a transaction size can be up to 128 bytes. And here we request 256 bytes. So we need 2 segments, and for each segment we need 2 transactions. That's technicality. But the ideal, we could have 4 transactions if the accesses of the threads in the warp were they had a good access pattern. They were sequential or in the same memory segment, which is not the case with this layout. But we could be 4x faster. And the question now is, how much slower did we measure from the memory bandwidth? If you see from 550, and we get around 140 is about 4 times. So essentially, we're not hitting the memory bandwidth because our warps has a really bad access pattern. So how we could fix that? So the fix is really easy. We should change the memory layout of the array. And instead of using the 0 major layout, we could use a Fortran layout so that columns are consecutive, are stored in consecutive addresses. We can do that. And there are 2 things now we could do. First, we need to change here. So it's basically instructing Numba CUDA to say your arrays are Fortran style. I'm going to also reduce a bit the size here to see just if this is enough. Well, it's not enough because I'm still storing the results in Fortran order. So what I need to do is also I need my A array to be also in Fortran order, in column major order. And actually, there is a little trick here that you have to do, because unfortunately, with NP random rand, you can't just say just set the layout. So what I'm going to do is I have it here. I always forget is as array. Yeah, I think it's like that. So you have to as array, and I think here you say order. I think that should be enough if I'm not mistaken. Okay, result validates. That's it. Our big arrays. Okay, so now look at the bandwidth. From 139, we're now memory bandwidth bound. So we're pretty good. We're 500 gigabytes per second. Generally, you don't expect always to reach. Also, this number we've seen is a bit lower than the actual that we could get from the performance counters, but it's pretty high. So if it's like 10%, it's 90% of the effective bandwidth we can get. So we're really happy. Now let's inspect a bit the kernel, what we have here, the matrix organization. and the matrix structure. So you can see that we reuse X for each row, right? So the array, the matrix A, we just go once through it, but the X array, we reusing it for every row. And it's very natural to think, okay, why then I should have it in the main memory and not just cache it in the shared memory? And it's a very natural thought. Actually, this is what we're going to do right now. On the other hand, from our analysis, we've seen that that we can't get actually more performance. We're just 10% from what we could ideally, maximum 10% for what we could potentially get. So we should not expect to get more from the shared memory, but let's do the exercise and see. And in fact, in newer architectures, yeah, let's discuss this. Let's see the algorithm, how it's going to be. So essentially now, one problem with a shared memory is that it's very limited. So it's only 64K. So you can't fit the whole X vector in it for sure. So what we should do is work in chunks. So the idea here is that you have a sliding window essentially, where basically the threads operate. And then the threads of the block, which is again one-dimensional, they serve a double purpose. First of all, they fetch the data from the X array into an array in shared memory, like this LX here. And then they compute the result on the whole window for this part of X, and they move that to the X array and they accumulate. And this goes on. And basically, each one accumulates first into a register, and then goes back to the Y vector. Let's see how it is. It's much more complex, as you were going to see, but there are some nice things we need to demonstrate for the shared memory. First of all, we need to see how much shared memory we need, because this is something you need to locate and some part in you need to explicitly locate the shared memory. Here, this part is the same. And let's see the kernel. So first we need to allocate the shared memory array. You pass the shape and the type as with a NumPy array. Now there is a small tweak here. The tweak is that this shape parameter must be constant. Okay, you will say in Python we don't have constants, but it should be something that is already defined at the time the kernel is cheated, and it should look like a constant, like here. Because, for example, and I really don't know why, if I do that, Numba will not compile, which you can probably see that this is also a constant, but perhaps it needs some compiler analysis to understand it. They don't do that. So in any case, that's something to keep in mind when you want to use shared memory. Now, the algorithm is a bit more complex. So we move into blocks. So we get the block, which is the same of the CUDA block, our thread ID in the block, and our num blocks. So here you see we're also using the I just to have the global index as of where we're gonna write, and the rest we handle it ourselves. So what happens here is this. So we have an outer loop going over the blocks, over this window, this sliding window, basically moves the window. And then first we move the data to the shared memory. And notice here how we do the offset. So it's B by B size plus, which is the offset, plus the thread ID. And then we bring that in. I'm going to talk about CUDA sync threads later on. So we bring the data in, and then we compute the product inside the block. And this is accumulated in that register. And this is really like before, exactly like before, except that we're not accessing X, but we're accessing the local version of X, the shared memory. And then at the end, we just do the final product and we compute. Here is exactly as before. Now, why we need this? So remember that I talked there's no consistency model or any guarantee about coherence. So in the level 1, so that means that although all the threads were executing the same, the threads were executing the same instruction, and we have multiple warps, and actually we don't know when the actual data of the threads will be written and made visible. So here we need to make sure that all the data, all the threads of the block have actually brought their data into the shared memory. That's why we need to put this barrier. It's a barrier inside the block. And here the same thing, we need to make sure that the computation from all the threads has been finished, so that then we can start again fetching data from main memory to shared memory. If we're going to omit that and see the effect. So the rest of the kernel is pretty much the same. So let's execute it. Okay. Okay, you see the performance is lower. Now, why is that? So one thing I've said before is that the shared memory, if you don't use it, it acts like a level 1 normal cache. That means that actually the caching we're doing here manually was already actually performed by hardware before, and actually it was done pretty well. All we do here essentially is introducing more overhead, because we introduce more overhead here in the kernel doing the second loop over the blocks, and we're introducing also overhead to fetch the data into the shared memory and so on. But no, that's not fetching the memory. Shared memory is not an overhead. But again, we introduce some loop overheads, which really affect the computation. And since GPU's cores are quite naive, let's say, and very simple, you should expect that little things might affect the computation, like happens here. So essentially, this is an unnecessary optimization, but it's good for demonstration purposes. And where you would need that. So you would need such an optimization use of shared memory in cases where you have temporal reuse of your data structures, of your matrix, of your whatever it is. So then in that case, you could bring in parts of your matrix or your data structure into the shared memory and reuse it as much as you can, and then dismiss it when you're done with it. And that's actually a very good example for that is the matrix multiplication kernel, where you can really benefit from the use of shared memory. So you again proceed in blocks in the matrix, and you compute a block, you finish with a block, and then you move on. And there is also here, there is a link with a Numba CUDA implementation that is, yeah, here, that shows that. So if you want to have a look. Now, let's try a couple of things that here in the exercise. What am I going to do? I'm going to reduce first the here just to be quicker, because it's not the purpose to see the performance anymore. Okay, let's remove one of the CUDA sync threads, right? And let's see what we have. Okay, didn't fail. We need larger matrices. Okay, you see it doesn't validate. So then it's a bit random. And it might validate or not, depending, because there is this race condition. But now I'm going to show you something else. Now I'm going to remove this, and I'm going to reduce the block size to 32 and retry and see if it fails. Oh, you see, well, it doesn't fail. Also, by the way, also notice the lower performance. And the reason that's mostly due to the occupancy, because our block is really very small now. So we are not taking full advantage of the parallelism. But nonetheless, it doesn't fail despite the fact that we don't have the CUDA sync threads. Now, the reason for that is that every operation in the GPU happens at warp level. So here essentially we have a single warp in the block. So all this operation will happen synchronously. So we don't need this synchronize, because there is no more warps. It's just a single warp. So a single warp will load the data, and as soon as it gets it, it will proceed. So that's why we essentially don't need the CUDA sync threads if the block size is 32. Okay, back. And then if you do NVProf with analysis metrics, you will see that now the overhead in this kernel is mostly due to these extra operations for the loops and the extra loops we have. So as a rule of thumb, if your kernel is, or operations are memory bandwidth bound, there's not much you can do, but you can just seek of alternative ways of storing your data, so that as to reduce the data transfers. That's the only way you can work around it. And then you should use shared memory when you have temporal locality in your accesses. So that's basically it. So we're just in time. I don't know if you have questions.
Vasilius, Enda has the hand up, but I'm not sure if there is a question. If there is, please go ahead, unmute your microphone and fire away.
Yeah, let me just, I should have the participants list. Okay, yeah. I unmute here.
Sorry, that was from earlier. I forgot to unraise my hand. I don't have a question.
Okay.
Okay, cool. Sorry about that.
Yeah,
so any questions, any? I don't know. Then if not, then we can break for lunch.
Once again, if you have questions that come up during the 1 hour break, just please write them into the Q&A and we can look at them afterwards. Otherwise, we'll see you back again in 1 hour from now. Thanks, everyone.
Okay, bye, everyone.